Yeah, so thank you for coming. It's really exciting to be here. It's a little bit dangerous to let me talk about particle physics because once I get going, I have to really work to stop. But I know what the time is on my laptop, and Kurt will give me the message when it's time. So today, what I'm going to do is, before I launch into some of the physics, I'm going to tell you why I'm up here doing the physics, or up here able to talk about the physics. We're going to go into what particle physics is, just to get a sense of it. How many of you, can you raise your hand if you have a definition for particle physics? If you think you would know what it is, particle physics? We have a couple people. Okay, so we're going to do a little bit of work to help define what particle physics is. I'll tell you about this incredible machine, the Large Hadron Collider, that lets us do the research we're doing, and then the Atlas experiment, and I have some really great pictures that I'm excited about starting here. So, when I first thought about things, which actually was pretty early, I think, in life, I assumed that there was kind of a plan, there was a straight line, and you move from one thing to the next thing. So a lot of you are in this middle school category here. And then, you know, what's the next thing you do? You know that you go to high school, maybe you go to college. And then if you decide you want to really go on in academia and become a professor or a faculty member, you know, you go to graduate school, you do a postdoc, junior faculty. Next thing you know, you're Einstein from here, and it's very straightforward. I didn't really take that path at all. Of course, I'm not Einstein, it turns out. I'm in this category right here still. But I want to talk to you a little bit about how things went for me. I grew up in a town of 500 people in Vermont. It was like, I don't know how many of you know Norman Rockwell paintings. That might not be familiar to you, but that's basically what it was like. My dad was the pastor of this Methodist church in the middle of the town, and everybody knew everybody's secrets. When I was in 8th grade, we moved to Morrisville, Vermont, which had 2,000 people and a movie theater, and a restaurant, a gas station, all right? I felt like I had seriously arrived in high school. I was pretty much a humanities person, meaning I loved to read, I loved to write, I was really into debates and arguing. I thought maybe I'll be a lawyer. And one of my teachers said, you know, in high school, 10th or 11th grade, you really should consider becoming a research scientist. And it really came out of left field. I don't know, what do you think of? When you think of a research scientist at this point in your life, what do you think of? What's the picture that comes to your mind first? Anybody? Yeah.
Me, like, I think of a research scientist as like somebody who does a lot of research.
Somebody who does a lot of research. Excellent. And what does that look like? I mean, anybody have an image of that? I can tell you what my image was. Not this. Except it was this, people looking at test tubes, different colors, and maybe they seemed happy, but in my mind, they were in a basement, they were definitely wearing lab coats, and I just had no idea why they would look happy looking at test tubes. I mean, when I thought research scientist, I thought, that just sounds terrible, that doesn't sound interesting. I had no idea what that kind of work would look like. And I really wanted to study the Constitution, maybe. I really was good at arguing, and I thought that was the path I was headed into. And then I took physics. A lot of you haven't taken physics. Anybody here taken physics? Had little bits? Okay, some of the people who are no longer in middle school have taken physics, which is good. It turned out I had been walking around for like 17 years, and I promised I'd been paying attention. I'd been paying serious attention to the world around me, and I had gotten almost all of it wrong. It was shocking to me to learn that I had such the wrong picture of how nature really is and what the laws in physics really are. And you know, maybe that's a depressing realization, but for me it was really fascinating. And I just want to give you one example that stuck in my mind because it was early. There's the example of like, you have a BB gun and a BB. I come from a town of 500, so we worked with BB guns when I grew up. So if you are on a flat surface, you're on a plane in the middle of a field, very flat, and you aim the gun and it's even. If you drop the BB and fire the gun at the same time, where you have a BB that's going out, it turns out that those two BBs hit the ground at the same time. Now, I don't know if that's shocking to you or not, but I thought the one that's fired from the gun has some momentum. It has something that keeps it in the air longer than the one that just hits and drops the ground. Does anybody have that intuition like I did, or none of you are surprised by this? Anyway, I had intuition that was totally wrong. And the more I learned about physics, particularly when I got to quantum mechanics, and I learned how crazy the world really is, where it's amazing anyone who's taken quantum mechanics can sleep at night, right? I learned more and more how wrong I was and how amazing the universe really is. So I was totally hooked on it. It wasn't my best subject when I started into it, but I was really hooked. By the time I got to college, I had a lot of fun. I was on the crew team, and I was a major in physics. And I had an opportunity. I was a work study student and got to work 10 hours a week in a lab. And Professor Melissa Franklin, who's a particle physics there at Harvard, she's now chairing the physics department, was hiring. And so I had a chance to work in her lab. And I got to work on the CDF drift chamber. And when I started learning about the detectors in particle physics, I totally was addicted to it. I'm going to show you a couple of pictures today that I think are amazing and tell you about the detector that I work on now, which is actually 6 stories high. It's really incredible. This is a drift chamber that has over 10,000 wires in it. And it's something that lets us, did everybody have a chance to see the cloud chamber out there? That cloud that forms, that lets you actually see evidence of particles traveling through it. The drift chamber is a different way that we can have access to particles traveling through, okay? This is a detector that lets us trace the path of particles that have charge. And it's just gorgeous. And the entire machine at the Collider detector at Fermilab outside of Chicago was just gorgeous. The electronics that were involved. And when I started to learn about how the machines worked, and I'm going to go into it a little bit, I realized that some of it's common sense, some of it's accessible. It's really, it's exciting to dive into that. This is some of the electronics. When I get to talking about the Atlas detector, I'll give you some statistics that just blow my mind. So I was hooked on particle physics as an undergraduate, not that we've defined it yet, but I'll tell you what it is soon. And went to graduate school at University of Rochester and did my thesis on the CDF experiment, where I had started working as an undergraduate. And now it's time for confessions. I'm being taped, but I'm just going to go for it and tell you anyway. At the end of graduate school, I was destroyed, absolutely destroyed. I had a great experience. I learned a ton. I was exhausted, and I was passionate about teaching. I was at a point where I thought, I just don't know if I'm capable of doing research. I don't know if I can keep doing this. Sometimes in life you find yourself in that position where you've worked, and you're just exhausted. So what I did was not rational. I went to a place where I was going to be teaching 4 or 5 courses a year, and 4 or 5 courses a semester, and the only physics teacher at the college. So I got myself much, much more exhausted. But had a chance to teach an awful lot of physics at Roberts Wesleyan College, a fantastic place, and remembered how much I love physics, and realized how much I missed the research. In spite of how much I loved the teaching, I wanted both to be a part of my life, okay? So I got a job as a postdoc, which I won't spend a lot of time talking about. And I moved to Geneva, Switzerland, where both of my children were born. This is just one of my children. Jonah was born when I was a postdoc. And I now have 2 kids. I came back to the US in July 2009. Jonah and Alina were both born in Switzerland. And Jonah is actually at this very moment getting his hair cut. So this is an appropriate picture, I think, to show you his haircut. Okay, so I had 2 kids. My husband is a research scientist here at Yale, and I came back to the US and continued with particle physics now as a professor, assistant professor at Yale. Okay, so that's me and why I'm here. I hope a little bit helpful. So now, particle physics. Let's see what we can do. A couple people raised their hand. Can anybody help me out in terms of a definition? Particle physics. Yeah.
Particle physics is really just the study of all physics.
I like that
I
very
mean,
much.
all physics of the particles, like different types of particles, bosons, quarks, and then there are different branches of the study of particle physics.
Excellent.
Mainly particle physics is a study of particles.
Excellent. Yes. A study of particles. And you should name some of the particles. Bosons, quarks. You may or may not have heard of those particles. Anybody have anything they want to add to that? Yeah, please.
How about that conundrum where particles also behave as waves? How do you handle that?
Okay. Particles and particles behaving as waves. How do we handle that? Well, let me tell you that we're extremely ambitious in particle physics. We pretty much would like to describe everything. And if you want to talk about things in terms of waves, that's fine with us. We have a particle description that we can use that's also valid. So let me tell you how we would phrase these questions. All right. certainly all of these particles, which are matter in the universe, we want to study everything about them and know what they all are. We want to know what are the fundamental forces, how can we describe them, and this is interesting, right? We don't just want to describe them, we want to describe them in the cleanest, simplest way possible, and we think that if we can describe them in the cleanest, simplest way, that shows the best level of understanding that we could manage for them. We want to know what is the content of the universe, and how is it that matter interacts through the forces? That's a lot of questions. I don't know if any of them make sense, but I can break it down for you as a particle physicist might think. Before I keep going in this direction, I want to ask you, why would you care about the answer to any of these questions? Because I would like you to care for at least the next, 30 minutes or so. Don't quote me on the number. Anybody know why am I so excited up here? It's not the caffeine I've had this morning. Why do we care about these questions? Yeah.
Well, go ahead.
Sorry. Mystery of the universe, like trying to find out everything.
Okay, trying to find out everything, that's just an interesting thing to do, isn't it?
Right.
I mean, do you think people have been trying to do that for a long time? Ever since the first people looked up at the stars and tried to figure out where are we? Who are we? How does everything work here? These are interesting questions. There seems to be something innately human about tackling these questions. Anything else? Or is that enough to keep us going for 30 minutes? Yeah?
Think about gravity.
Gravity. Yes, gravity. Everybody experiences it. We know it exists. How does it work? It's important for us to understand things that we have to deal with in life, right? Definitely. Okay. I think hopefully that will carry us through the next 30 minutes because I'm going to show you a couple of pictures that might not be familiar, okay? Inside of particle physics, the things that we know, the things that we've categorized and understand, we can describe within the standard model. And we break up all these particles into different categories, right? We have some quarks, we have some leptons, and we have some forces. I'm not going to spend a lot of time talking about these individual particles very much, sorry. But I do want to talk about the forces just really quickly. We believe that there are 4 forces in nature, all right? Electromagnetic, weak, strong, and gravity. Let's start with the top one. When you hear the word electromagnetic, anybody? Lightning, okay, electricity, refrigerator magnets. I think you would believe me if I told you that electromagnetic forces are real, okay? That's an actual force, we're there. How about the weak force? Have you heard of the weak force before? Yes, sir. Do you know what it is? Could you define it? I mean, you've heard of it.
It's really the best way to describe it is the force is responsible for the decay of the neutron.
Excellent. That's exactly how I define it. Okay, it's not a push or pull force. That's fantastic. Actually, can I steal that? I think I'm going to steal that for the future. And it's on video. This is making me a little bit nervous. This is recording. Right, it's not a push or pull force. It's a decay force. Radioactive decay. If you've heard of radioactivity, that's because of the weak force. Now, the strong force. Has anyone heard of the strong force? You have.
It's the force that keeps protons from moving away from each other because they're all positively charged.
Unbelievable. Unbelievable. Excellent. Okay, so have you heard of the strong force? Listen, when I took chemistry in high school, which some of you are going to do at some point, maybe you've actually heard of protons before. You're going to learn about an atom at some point in your life. And you're going to learn, have all of you learned that things that are positively charged and negatively charged are attracted to each other, and things that have the same charge don't like to hang out near each other? You have. Okay, excellent. So that's yes, you've heard of this. All right, so we're starting from that point. You're then going to learn that inside the atom, all of the protons that are positively charged are crammed in really close to each other in the middle of the nucleus. And when I learned that information, I'm confessing to you right now, I wrote it down in my notebook and didn't worry about it until a couple of years later. Oh man, wait a second, why are these things that are all positively charged that really do not want to hang out next to each other crammed into this tiny area of the nucleus? It really doesn't make any sense if you think about it. Gravity isn't strong enough to keep them all pulled together. It takes something very strong to pull these things together. And sometimes you get lucky enough so that the language that you use for your work actually makes sense. The strong force is a strong force, and the mediator, the carrier of the strong force, is named the gluon. Isn't that awesome? And that glue not only keeps the protons together inside the atom, but keeps the quarks that are inside the proton together, okay? Gravity. Gravity isn't actually in the standard model of particle physics. What that means technically is that we have not incorporated a quantum theory of gravity. We don't have a field theory of gravity. Okay, bummer. Is that kind of embarrassing? I mean, gravity, all of us know about. It's been around for a while. What's our excuse? Why am I standing proudly in front of you saying this? Let me do just an experiment with you. How strong is the gravitational force between my two hands? When you have your hands like this next to each other, you know that gravity is an attractive force. Masses are pulled toward each other, or I am pulled toward the earth because of gravity, right? But I don't even feel that force between my two hands. Can you feel the gravitational force if you put your two hands next to each other? I don't even feel any attractive force there, right? But you're going to learn at some point in life, well, actually right now, turns out your hands are mostly made out of space, but you can't pass them through each other. It's the force of electricity and magnetism that keeps you from pushing your hands through each other, even though it turns out that the matter inside of your hands means it's concentrated in ways that are mostly space. The force of electricity and magnetism is incredibly strong compared to the gravitational force, all right? So there's our excuse. It's incredibly weak, gravity is, compared to these other forces. And we're on it, we're working on it. And since we're doing caveats here, it turns out that about 96% of the universe isn't part of the standard model. We have dark energy, dark matter, things I'd love to talk about more. So if you're thinking of going into this field, don't worry, there's plenty to do. We have a lot of work to do, okay? But how do I know that any of these particles exist? I showed you a list of particles, quarks, leptons, gluons, and bosons. How do I know that any of these exist? Do any of you have evidence for particles existing? I mean, do you believe this stuff when you hear it? I hope you're taking my word for it to some extent. Did anybody see the cloud chamber? Yeah. You did. So you saw evidence of tracks of particles or something there, right? What's that? Okay. I want to tell you just about a little bit of the history of particle physics so that you have some grounding here when we go into talking about present-day accelerators. Scientists have a reputation for really doing crazy things. It's a proud reputation for doing crazy things. Back in the early 1900s, people knew that there was radioactivity. And the Earth was the source of radioactivity. Okay, we know that now as well. There's radioactivity around. I don't know if you guys have radon measurements in basements that you're aware of. Anyway, people were doing experiments and they wanted to understand, what is this radioactivity? How does it work? How strong is it? So they had detectors that could measure radioactivity. And they were bold. And they said, okay, if I climb up to the top of a mountain, I'm further away from the mass of the Earth, so the amount of radioactivity that I can measure should go down. And then they weren't satisfied by climbing to the top of the mountains. They actually went up with their detectors in balloons, okay? They carried their detectors in balloons with them to try to see how that radioactivity changes as they got further away from the surface of the Earth. In 1912, Victor Hess got up to 5,000 meters in a balloon. That's very far up there. And he realized, shockingly, he was going up in the balloon, the level of radioactivity was going down as he got further away from the surface of the Earth, and then all of a sudden, the level of radioactivity started to go up. And as he got further up, he saw that it continued to climb. And that was the discovery that we also have radioactivity coming at us from the universe. Okay, that was the discovery of cosmic rays. Not only do we have a source of radioactivity on the Earth, but as you get further away from the Earth, and the idea there was the atmosphere is blocking a lot of that radioactivity coming in from outside. But as you get further up and have less atmosphere between you and the universe, you start to sense some of that radioactivity. And in 1938, Pierre Auger put detectors on the tops of mountains that were separated by some distance. And he learned that not only is the radioactivity coming at us from the universe, just single particles coming down, but there were actually showers of particles. And this is a nice graphic that describes what happens as you have a high energy particle coming in from the universe. There are showers of particles. A lot of the activity that you were seeing in the cloud chamber that wasn't near that source was because of cosmic rays. We have cosmic rays passing through us all the time. When I was in graduate school, well, so now we still send balloons up in particle physics to try to learn more about these cosmic rays, and they go up much higher. We don't have people in them anymore. When I was in graduate school, I was tempted a little bit to change experiments to the Pierre Auger collaboration. They have a grid of detectors that are spread out over a very large distance. It turns out they're over, they have almost 2,000 of these tank detectors over 3,000 square kilometers in Argentina. I went to a talk by a Pierre Auger scientist. Do you know what they talked about? Cows. One of their biggest problems in their experiments were animals wandering over to the experiments and actually messing things up. So I thought, wow, that is just so cool. Here you are doing particle physics and you're talking about cows right now. And they had to go and learn about the different animals and how to protect their experiments from the animals and not interfere with what was happening. Yeah, it's very funny. Okay, that was just an aside. We have, what I do my work in is actually using accelerators. It's nice that nature gives us this source of cosmic rays so we can learn about these elementary particles. They're coming at us from the sky. It's also nice to have some control over them and fire particles at each other and be able to measure the results of those collisions and learn more about the particles. But we haven't stopped being crazy in particle physics. Look at this picture of the Katrina experiment coming through a town in Germany. They were talking about the clearance on either side of those houses at the level of millimeters. Okay, this detector was moving very slowly through this town, in order to get it to its final location. This is part of the experiment that I'm on, the Atlas detector, actually crossing the street in Switzerland. You can see that in the background. This is a pretty cool picture. Can you see that picture well from where you are? All right, well, if you go to graduate school in physics, you can think back to this moment, or actually graduate school in anything in life. You can think back to this moment when you're doing something that may seem a bit tedious. So this is a giant tank that's being filled with water, and there are photomultiplier tubes that help you in the detection of neutrinos is what they're trying to get. They're watching the interactions in this giant tank of water. What's happening are these little people in the boat are very slowly being raised up as the tank is being filled, and they're going around in the boat cleaning all of the photomultiplier tubes, which I think probably was really awesome for a while. But after a while, there are a lot of photomultiplier tubes. Before I launch into the Large Hadron Collider, this is the end, my last introduction to particle physics slide. I think it's important. The reason that we do this science is because we're really excited to learn more about nature. It doesn't really have a direct practical application. We're not trying to build anything out of the particles that we're colliding. But there are a lot of positive benefits that come out for society because of the research. I think it's really important to at least mention that. The National Science Foundation tells us that about 0.4% of our GDP goes towards basic research. And it's helpful to know that there are outcomes aside from changing textbooks, which I think is fantastic. And you never know with new discoveries where that new information will lead you. But there's an awful lot that accelerators are already doing for us in society. Okay, so two more things that I'd like to do this morning. I haven't mentioned the Higgs boson yet, so we're going to go there, and that's really motivated by thinking about the Large Hadron Collider. And the Large Hadron Collider, this is the machine that creates collisions that I study along with many of my friends in the Atlas experiment. Okay? The Large Hadron Collider. So let's think a little bit about how it works. It's 100 meters underground. The Alps are on one side, the Jura on the other side, and the protons that are circling around here spend most of their time in France and a little bit of their time in Switzerland. Okay? Crosses over into Switzerland, even though the CERN site is actually built in Switzerland. The goal of the Large Hadron Collider is to bring protons to high energy. And I describe myself as a particle physicist or a high energy physicist. Why do you think if I'm studying elementary particles, Do I need to be at high energy? Why am I interested in high energy? Anybody have any ideas? Yeah.
You said earlier that the cosmic rays bring showers, and maybe the showers raise the high energy, the showers, and the showers raise.
Okay, that's an excellent point. When you go to, so he was mentioning, the high energy, I mentioned that the cosmic rays that come in are at high energy, and it's not just one particle that comes in. When it starts to interact with the atmosphere, there's a lot of energy, and it creates a cascade of particles. And he pointed out that, you have a lot that you can study there. That's certainly a fundamental reason that we would go to high energy, because you have all of this energy available that can create a lot of different particles. And thank you, that was perfect. It leads right into my E equals mc squared. People heard of this equation? E equals mc squared. This is the non-relativistic version. Yeah, excellent. It turns out that energy on this side of the equation can be thought of as a potential equivalence for producing mass on this side of the equation. This C here stands for the speed of light. Okay? So you have energy on one side, you have mass on the other side. If I have a lot of energy, I can create a lot of mass. And the particles that I want to study, a lot of them have a lot of mass. It turns out the Higgs boson has mass, and if I want to create a Higgs boson, I have to have enough energy that I put in order to get a Higgs out. So that's really important. We talked about that strong force that holds the proton together, or holds bunches of protons together. In order to break those bonds inside protons between the quarks, anything where the strong force is working, it takes a lot of energy in order to break those bonds, okay? So that's another reason that we want to go to high energy. And the other reason to go to high energy is we're in the game of discovery, and when you climb up to higher energy, it's like climbing up a mountain and looking around. You can see more from up there, right? We talk about it in terms of covering more phase space. Going to high energy allows us to discover new things. In terms of how we get to high energy, we try to increase the kinetic energy of a particle. So what is that? The energy of motion. When I think about this, I like to think about gravity, because gravity is something I understand pretty well. If I drop a penny from right here, it's going to get faster the longer it stays falling, right? If I drop it from the top of a building, it's going to be falling for a longer time, and it's going to pick up speed. You're keeping an object moving in a gravitational field. The longer you keep an object moving under the influence of gravity without stopping it, the faster it gets. What we do is we put particles in electric fields, charged particles in electric fields, and we keep them there for a long time. We have two different kinds of accelerators that give us these electric fields. You have the linear accelerators, where it's a straight shot, boom, send a particle heading out in that direction. You can smash it into something at the end, or if you're really excited, have two linear accelerators, boom, firing the particles at each other, and you get even more energy in the center. Or you can have circular accelerators, which is what the LHC is. So why linear versus circular? If you're making that decision, you're planning the next accelerator. Yeah? Okay, you're thinking about cost. It depends on how you design it, but that's a huge reason that you care one way or the other. So yeah, if you have a circular accelerator, you not only have to speed the thing up, but you have to steer it, right? And steering it needs magnets. And so depending on how you design things, circular accelerators can be expensive, and magnets can be expensive. That's a great point. The benefit of a circular accelerator is it's like you've cheated. You keep the thing steering around, and it keeps staying in the field. It keeps staying in the electric field. It gets faster and faster and faster and faster, right? As opposed to just having one shot where it flies by and you've got to do that acceleration in this piece. Okay. So, yes, we talked about that. A couple of numbers. We accelerate protons to point, let me see, 9999999. Is that the right nines? You can count this on the screen times the speed of light. These things are really screaming, very close to the speed of light, okay? It's 27 kilometers around. 27 kilometers around. Do you have any sense of how big that is? Has anyone been to the Grand Canyon? I hadn't been until I was actually way past college. You've seen pictures. Here's a picture of the Grand Canyon. You know that it's big, right? This is me and my husband on our way to my postdoc at Stanford before I headed out to CERN. 5 o'clock in the morning, if you go to the Grand Canyon, 5 o'clock in the morning, that's the time to go. Seriously, it gets really crowded at the Grand Canyon. very early, gorgeous sunrise at 5 a.m., right? Okay, so this is the Grand Canyon. Here's a map of the Grand Canyon. The LHC circumference I've drawn on here so that you can see it's the scale of the Grand Canyon. And if you haven't been, that may not sound big, but if you have been, it is big. I thought about comparing the LHC to oceans. I thought about comparing it to sky. I thought about, anything that's that big, I can't really keep my head around it. But the Grand Canyon is a big thing that you can kind of keep your head around. And the LHC is about that big, buried underground. The thing about the LHC and the Higgs is we have just a slight problem in the standard model of particle physics, and that is all of these particles mathematically, without any intervention, should be moving at the speed of light. The speed of light, it's a speed limit that we know about, right? Photons, the light-carrying particles, moving at the speed of light. The question that we have in particle physics is, why is it that we all can exist right here? Why are all particles not moving at the speed of light? It turns out particles have this quantity that we call mass. They have a property we call mass. And the fact that they have mass keeps them from moving at the speed of light. And the LHC was built in a way that would let us either find or rule out one idea for giving particles mass. The Higgs boson is the particle that gives us an explanation for how things get mass. Okay. And I promise I'm not going to spend a lot of time. I love this plot very much, but I understand a lot of you, this is not a helpful plot. But for those of you who have had some background, this picture right here is absolutely the motivation for the LHC. It contains on it, we're going hunting for a particle, we don't know what the mass of that particle is. So it contains on it possible masses on this axis that the particle could be at. And this is a picture before we turned on the LHC. This yellow stuff that's blocked out shows you where other experiments had already looked for it and not seen it. And this point right here tells you where it's predicted to be, all right? So the picture before we turn on the LHC is we have a prediction for the mass of the of the Higgs right here. It's already been looked for at other experiments and not found there, and the LHC is going to let us cover this area right here. All right, that was the motivation for the LHC. There are many, many, many other physics projects going on at the LHC, a lot of them that my group is involved in, but the Higgs was a central motivator. And just to convince you that this is something that's exciting to a lot of us, this is a picture in the Atlas Control Room in 2009 of the first collision event that was captured on the screens in the control room. You actually can go to the control room webcam and look at any time and see just how excited people are compared to this. It's updated every 30 seconds or so. But some of us get really excited about electrons. So, and protons and, Higgs bosons, of course. So that's the Large Hadron Collider. It's a circular accelerator. It smashes protons together at a couple of different points. And one of the points where it smashes protons is the Atlas detector. The goal of a detector is to completely surround the collision with technology that gives you information about what happened inside of that collision. And I'll talk about that a little bit more with this picture, okay? So here it is, the Atlas experiment. This is to make everyone feel better about acronyms. This is as tortured as it gets. If you're ever designing a group name, don't worry about where you pull the letters from for your acronym. You can take it from the end, you can take it from the middle. You can have an acronym inside your acronym, right? Feel free. Somebody's been worse about it than you will ever be able to be, probably. But this is a picture. You have protons coming in, and they're colliding at the center of the detector here, and the Atlas detector is built around that collision point, and when you have the protons collide, it turns out, remember the picture that we saw of the cosmic rays coming with all those particles? We have hundreds of particles that come out of the collision of the parts of the proton that collide at the center. One of the things I love about particle physics is how international it is. There are 3,000 people on this experiment. My view of the research scientists sitting alone in the basement with no windows was so far off in terms of what I actually do. Though I do spend some time by myself in front of my computer thinking and getting work done. I'm also working with 3,000 of my best friends from all over the world. South Africa has also joined the Atlas experiment. There's a group there, so this map is a little bit outdated. It turns out it's really hard to have a meeting with all these people, even on the phone. A lot of times I'm up at 3 o'clock in the morning. Just last week I was up at 3 in order to sign in. Australia, Japan, it's complicated. So here it is. Here's Atlas before the innards were inserted. This is kind of the shell. The muon detectors and the toroidal magnets on the outside. See this person standing here? The Atlas detector weighs as much as the Eiffel Tower. I don't know if you've seen pictures of the Eiffel Tower. It's 6 stories high. It's really complicated. Do you see the people here? Show you the scale of how big it is compared to those people. You can't go down and visit it now because it's been running. First of all, you don't want to be near where the collisions are happening. It's 100 meters underground for some good reasons. There's also some radioactivity that builds up that it takes a while for things to cool down before you go back in and can check it out. But probably this summer, we have a shutdown coming up soon and people could go down and see it. If you happen to be in Switzerland, I'm going next week, but I know not everybody has a reason to travel. There are different kinds of detectors. We have what we call tracking detectors on the inside, calorimeters, and lots of different technologies. I want to flash up some pictures because, as I told you, this was really the thing when I started working in particle physics that totally pulled me in, seeing how these detectors work. Can you see the pictures of these, you know, the light coming out in these fibers? There's just so much cool physics that's in this. I actually worked on the part of the experiment that's called the trigger. We have every 25 nanoseconds, 40 million times a second, there are bunches that can collide at the center of the detector. And we can only keep information about 200 of them. So you have to decide what's interesting. Here I am on shift in, when was this? Well, I'm very pregnant, almost 9 months pregnant here, so it must have been 2008. I was on shift in Switzerland, living in Switzerland, right? I was there for 4 years, and my family was in the US. And so I used to call them as much as I could over the computer, but I emailed them a couple of weeks before this picture was taken. I said, hey guys, I'm gonna be in the control room. I'm gonna be on shift, and there's a webcam. Go to this website, and you can check it out. You can see me on shift. 3 weeks later, I got an email from my younger brother, Micah, well, name since it's in the video, that the subject of the email was hungry. And if you zoom in, you can see my hand kind of like this. I don't have to zoom in for very good reasons. My cheeks are out to like here. Another great thing about particle physics is we don't work with materials that when you can't eat in the lab. I don't know what I would do if I couldn't eat when I was doing my work. Particle physics, we're okay with that. It's just computers. So yeah, my cheeks are like out to here. You have to be really careful what information you send to your family. But it was nice to be able to stay connected to them. So here I am in the control room getting ready for the run that was coming. We have thousands of computers set up to help us make decisions about what kinds of events are interesting. And just to show you some of the things that we're looking for black hole events, we're looking for Higgs events. You can ask yourself, how do you know that you've actually seen any of the things that you're looking for? We make nice, pretty pictures and also do really detailed analyses of, you know what, if we had created a black hole in the middle of our experiment, which we hope we're doing, we just haven't measured yet, this is the output that you would get from your detector. This is the kind of information, all these particles streaming out that you can track and see in the detector in this way. So if we see something, a signature that resembles this, that we can pick out from other pictures that we would get out, we would have evidence for a black hole event. And this is a picture that shows you what a Higgs event that's simulated would look like, one possible Higgs event. We use some of the particles that are particularly easy for us to pick out in the detector. They're called the lepton and the muon in particular. Let us pick out from this mess. Do you see this mess? That's another picture, a way to look at the Atlas detector. You're looking at it head on and seeing all the energy deposits that are created by the particles coming in. You have to pick out something that's pretty, that stands out from all of that mess. And we use the physics that we know in the standard model to help us do that. Okay. On July 4th, a couple months ago, there was the announcement from 2 of the experiments of the LHC, my experiment with someone else, of the discovery of a new particle. Okay? So here we have Fabiola, the spokesperson of my experiment, and Joan Candela, who's actually an American physicist in California, who was a spokesperson of the other experiment, at that announcement of the discovery. And this is a picture of very tired Yale undergraduates. We had David, Katie, Maddie, this is Ariel, Catherine, Lizzie, Jerry, Ari. They camped out the night before. They rode their bikes. They were living in France, not very far away from where the headquarters were in Geneva, Switzerland. And they rode their bikes at like 11 o'clock at night, and they camped out in front of the doors of the where the announcer was going to be, kind of like a rock concert, you know, where if you really want to get in, you get there really early. And there were a lot of people that were camped out, and they had to fight for their position in line. And there was even a fire alarm that went off at like 3 o'clock in the morning. And you know, all of these obstacles they overcame. So they're looking very tired right now, but they had a lot of energy that was expended getting into it. This is before the announcement came out. But basically, the idea is at this point in the research, and this is I'm almost done, guys. You've stuck with me well. At this point in our research, we have a particle that we've discovered. We've picked it out because of the signature, the way it looks in the detector. It's looking an awful lot like the Higgs boson, but we're not ready, I'm not ready to say it's definitely the Higgs boson that we predict. I think there's more work that we need to do in order to know that it's not something that looks like the Higgs boson. We don't want to be wrong here. We don't have a lot of LHCs in order to have a lot of opportunities to get this right? But it looks like we may have an answer for why it is that all of these particles aren't moving at the speed of light, for what is slowing these particles down, and what is giving us this idea of mass. Beyond the Higgs, I think the LHC, the Large Hadron Collider at CERN, it really can revolutionize what we know about physics, because the Higgs is not the only thing we're after. By studying these fundamental particles and going to higher energies, we think we're going to be able to, we think we're going to be able to learn a lot about physics. We hope we can. But even if there isn't a lot else that is discovered out of the LHC, even though we've already learned a tremendous amount, it does look like we may have this Higgs boson in the standard model. And thank you very much. I know this stuff wasn't all easy. I really appreciate your attention and your time. It was really fun for me to talk about.